Okay, hello everyone again. So, since I will be talking about non-interactive zero-knowledge proof systems, which may be rather unfamiliar to a lot of you, let me start by introducing first what the general goal in proof systems are, and then we will see what we do about them in the quantum setting. So a proof system in general, or in the cryptographic, well, the way we see proof systems in the cryptographic setting is the following. Imagine you have two entities, a prover and a verifier, and the prover knows that a certain statement X is true. In cryptographic examples, this may be, for example, something like X is a ciphertext, and the statement is that it's a ciphertext that encrypts 0, or something like that. Or if we would want to connect it to the talk before, it may be that the prover has done some homomorphic operation on some ciphertext, and he wants to prove that indeed he did the right operation, so some operations that are prescribed by the setting. And proofs like that are very important in various settings, because often you do something and you want to convince everyone else that the data you send out afterwards is the correct data, so that other people can process that data. And if the prover wants to convince anyone of the fact that the statement he knows is true, he needs to have a so-called witness. So witness is any value that allows us to easily check that the statement is true. So for example, if the statement is, this is an encryption of a positive number, then the witness may be the decryption key, because with the decryption key I can just decrypt and check whether it's a positive number. Now, if the prover wants to convince the verifier that the statement is true, the easiest thing he could do would be just to send the witness to the verifier, and then the verifier could check. However, we want to impose one more very important restriction, namely, we do not want to reveal the witness. I mean, think again of that the witness is a secret key. We don't want to send out the secret key just in order to convince people that our ciphertext is correctly formed. So in a proof system, we have two requirements that are not trivial to achieve at the same time. The first is soundness. The verifier accepts only true statements. The definitions, the precise definitions are more subtle. It's actually up to small errors and so on, and there are many variants. But for understanding this talk, it is sufficient to kind of accept that that's roughly what we want. For those in the know, we will actually be talking about proofs of knowledge here. But additionally, we want that the verifier learns nothing. That's the so-called zero-knowledge property, which is quite non-trivial to define, and therefore I will not even try to define it, because most of the time I will only be talking about the soundness. But trust me that there are definitions there and they make sense and so on. So if we want to achieve those two things at the same time, so I cannot prove something wrong, and the verifier, I can convince the verifier without the verifier having any clue about my secrets, one can see that you can't just send the witness. So in general, a proof system will consist of a number of rounds of interaction between the prover and the verifier. And that's basically what we mean with by a proof system. Some interactive protocol with a lot of interaction back and forth, and in the end, the verifier is convinced. So let me then introduce two classes of proof systems that will be important in the following. The first is a sigma protocol. A sigma protocol is a proof system that has a very particular structure. Namely, in a sigma protocol, we have always exactly three messages. The first going from the prover to the verifier, called the commitment. The second is the challenge in the other direction. And finally, the prover has to give some response to the challenge. And one important limitation is that the challenge has to be just a random value. So they can, the commitment, the response can be made like according to very complicated rules, but the challenge has to be a random value. Now, what's the advantage of having this additional structure? Well, one big advantage is that sigma protocols have very versatile combiners. Namely, if you have, for example, sigma protocols for two different statements, then you can make a sigma protocol for the logical disjunction of these statements, or for the conjunction, or for something like this. So you can make very easily then a sigma protocol that A and B holds or C holds, without even revealing which of the two holds. So that's one of the big advantages of sigma protocols. And also due to their fixed and simple structure, sigma protocols are much simpler to analyze in many settings. Unfortunately, on their own, they give rather weak security guarantees, namely either the probability of being able to cheat, at least when we execute it only once, like the soundness, is relatively high, or they are not actually zero knowledge, but something weaker called honest verifier zero knowledge. So there are some challenges here. I'm not going to go into them in detail. And then another variant are so-called non-interactive zero-knowledge proofs, which are the ones that are the goal of this talk. So they have an even simpler structure. There's the prover. It sends just one message to the verifier, and the verifier checks and then accepts or rejects. So it's almost like a mathematical proof. Having that is very nice for two reasons. The first is they behave much better in settings where we have concurrency. So if I'm sending various proofs about various things at the same time, nothing bad ever happens with that, for the simple reason that, well, in comparison to the Sigma protocol, I can have some non-trivial interleavings between the messages from one commitment, from one protocol and the other, and they can kind of get mixed up between protocols and so on. And it turns out that makes things very hard and very annoying. But here you cannot have any interleaving, and the interleaving is the thing that makes the things annoying, and therefore, in concurrent settings, non-interactive proof systems are much nicer. And second, you have this offline capability. So you can, for example, take your proof and store it on the hard disk, or you can take your proof and encrypt it and send it via email, and so on. So you don't have to have these live responses depending on each other. And that makes non-interactive zero-knowledge proofs much nicer to use. But they have all come also with a number of disadvantages. The first is they don't actually exist, at least not in the form I've drawn them here, because they will always need some additional setup that supports them. Namely, we have basically the two well-known choices what we can do in order to actually be able to construct non-interactive zero-knowledge proofs. One possibility, called common reference string, would be that we need some publicly known random value that is known to everyone on the world. So both of them also depend on some random string that is given for reference to everyone. But there the problem is who chooses it. Yeah? Whom do we trust enough that this string is indeed random? Because you can, if you choose this string maliciously, you will be able to cheat in this proof. And the second variant is to use a so-called random oracle. What is a random oracle? A random oracle is some idealized modeling of cryptographic hash functions. So you may have a protocol that uses hash functions like SHA-3 or something, but you cannot analyze it because it's too complex. SHA-3 has a lot of weird structure in it, and you need to understand it. So one simplification is to say, I prove the security of my protocol not using SHA-3, but actually saying there's a random function, a uniformly randomly chosen function, that's my hash function, and I prove that the protocol is secure under the assumption that that's my hash function. And then I heuristically assume that SHA-3 is so unstructured that any protocol that is secure that is secure with a random function will also be secure with that particular hash function. This is just a heuristic. You can even find examples where this is wrong, but it has proven very useful in cryptography, and I'm not aware of any cases where this breaks down when you actually don't actually try to make it break down. The second disadvantage of non-interactive zero knowledge is the lack of nice combiners. Yeah, you can't just in a general way take two non-interactive zero-knowledge proofs and make a new non-interactive zero-knowledge proof out of them for the OR of the two statements. And it's more restricted in the set of language it covers, so it's not as easy to build them. And there is some relatively old result that combines the best of the two worlds. It's the so-called Freecharya construction. And what it does, well, I think in the original paper it didn't do it in that generalized way, but basically if you take the construction and analyze it in terms of more modern concepts, what it does is it takes a sigma protocol and transforms it into a non-interactive zero-knowledge proof. And it does it in a very simple way. To produce the non-interactive proof, the prover produces the commitment, as usual, but then it can't talk to the verifier. So who gives us the challenge? Well, we get the challenge by just hashing the commitment, and that's like a random value. And then the prover produces the response. And the verifier, to check this, just also hashes the commitment and checks whether this is a correct interaction. This is now has a lot of the advantages of both settings we had before. We have the ease of use of non-interactive protocols. We have versatile combiners because we can just combine our things together before we do the transformation. So we build up some sigma protocol for complex language and then translate it. The analysis is simpler because we analyze the protocol itself here and then use it in this setting, and so we can always stay on the simpler side. The only thing that we didn't get rid of here was the use of the random oracle. But that's something I'm not going to get around in this talk either. So since I'm not going to get around this in this talk, you may wonder, so what am I going to do? Because that seems to be the last disadvantage. No, I'm not answering that yet. I'm still talking about some advantages. Just a side remark, there's also one more thing that Freecharya also gives us. It actually doesn't just give us proof system, it also gives us signature schemes. You can see that the thing we construct is a signature scheme. Okay, but now what's the problem? Well, the problem is we do not know whether Freecharya is quantum secure. So it's a classical protocol, but we may want that it is secure if the attacker has a quantum computer. And we have no proof of this fact. I'm working on that a bit, but it's kind of tricky, and so far I don't know what to say. We even know that in the full generality, we won't be able to prove it. So there we have impossibility results that show that relative to some oracle, it is impossible to prove Freecharya correct, to prove that it's actually a proof system. That doesn't include that we can't show some security results under extra conditions, but so far nothing is known. And the reason why things work so badly is that the security proof actually uses rewinding in the communication with the random oracle. And that's really hard to deal with. So we may ask, can we get around that? Can we make a quantum secure construction that achieves the same thing as Freecharya, but does not involve rewinding so that we can use, that everything gets simpler? Well, there is, actually I'm a bit low on time, so let's skip, no, let's not. So there is one scheme by Fischlin, classically, that actually avoids rewinding. And the trick is that it uses something called online extraction. It runs the prover, and then it looks at the list of all the random oracle queries that the prover did, and can then, from looking at how it communicated to the prover, just from looking at these things, extract the witness. And now the reasoning is, if we can extract the witness, then the witness must exist. If the witness exists, the statement to be proven is correct. So we always have this hypothetical construction of an extractor that can extract, that has to extract a valid witness from what the prover does. Unfortunately, we can also prove that there is no security proof in general for this. And the reason is that the concept of the list of all queries that are made is not well defined in the quantum settings if the queries to the random oracle can be in superposition, because we are not allowed to measure them. So without further ado, let me show you how we solved that. the idea is to actually also extract the witness from all the queries that are made, but actually just by looking at the final result. So what we do is we have the prover who communicates with the random function, and we make this random function invertible. We will see in a moment why we can do something as weird as that. And then the extractor who gets the proof from the prover just looks at all the hash values that are in the proof, inverts the random oracle, and gets the witness from that. That's the basic idea. So how can we achieve this idea? Here's the protocol. So what we do in the protocol is the prover picks a lot of commitments, and then for each commitment, he picks a lot of challenges and computes the corresponding responses. So all this would be very convincing because each kind of line is already a proof in a sense. But if we reveal that, we will actually reveal too much about the witness. It will not be zero knowledge. Therefore, we use the random oracle to hash all the responses. And now this thing we can reveal without losing any of our zero knowledge property, but it will not convince anyone either because the responses are all hidden. So what we do is we take this whole thing as one big string, hash it, and the hash values we let indicate which of the responses we should reveal. So from each block, one of them is chosen by this hash value. And all this is our proof. We send it over the network non-interactively, and the verifier checks it. It's like he checks whether the responses we opened form correct interaction, and whether we opened those that we should open according to this. So security analysis, with high probability, at least one of these commitments must now have at least two valid responses. Because if each has only one valid response in these hashes, then the probability that the ones we are told to open from the hash function, that those will be the few ones that are correct, will be low, and the prover will fail. So if the prover manages to open one response in each block, then at least one block should have two responses. And these responses can be gotten by inverting the hash function, by inverting them all. So the extractor can get these two responses, and the properties of a Sigma protocol, which I skimmed over, tell us that from having two responses, we can get the witness. And that proves that this must be a proof, because if a witness always can be extracted, it must exist. Now, the problem is, in general, random functions are not invertible, at least not efficiently. So, and they shouldn't be. But the trick we use here is, in the proof, not in the actual construction, but in the proof when we talk about this hypothetical extractor, we replace the random function by a 2q-wise independent function, for example, a polynomial. If we want to invert it, we ask, well, I should first say it's known that this cannot be told apart by the adversary. That's a result by Gendre. And we know that what we need to find, however, is an invertible 2q-wise function. And none are known, but we can get around this by using degree 2q polynomials, which are almost invertible. We find 2q pre-images, and turns out the whole construction still works. And that leads us to the final result. If the Sigma protocol has these two standard properties, then the protocol we construct is zero knowledge, and it is sound. It is even simulation sound online extractable for those in the know. And I'm skipping the further result because time is low. Thank you for your attention.
Yes, so thank you very much, Dominique. Questions? Yes, Gilles?
Maybe I just didn't pay enough attention, but I failed to see where you get quantum proofness here, as opposed to the classical version.
The reason is that when we do not use any, I mean, the proof looks very classical at the first glance, but it doesn't use any tricks when we analyze it, like rewinding and so on. So that's why the proof goes. I have not told you at all how we do that. I would use another half an hour for that. So there's a lot of difficult technical stuff here, but I just don't have the time to go into that. So you have to take it on trust that I can analyze it. And what you can understand from what I showed you is how I circumvented the rewinding.
Yes? Charlie?
Well, I haven't kept up to date with random oracles, but for this invertible random oracle, couldn't you just use a random permutation?
Yes, but that would probably not be a good modeling for a hash function. So that's the first problem. And you would also then need to think about how you justify that if you use one that is, you need also to justify why the extractor actually can efficiently invert it. So if it's just a permutation, you don't have that argument. So and if you actually have an invertible random permutation, then you lose the zero-knowledge property because everyone can look into these hash values. So you actually would like to stick to actually a random oracle and only in the proof, like as a hypothetical concept, make it invertible and still efficient. So that's the reason why you can't just switch to a random permutation.
Okay, maybe one more question? Yes?
Just to continue on Charlie's question, then couldn't you use a random function inside a Luby-Rakoff argument to turn it into a permutation?
Perhaps, but as far as I know, Luby-Rakoff has not been shown to work in the quantum setting yet. We have thought about it a bit and so far have no clue how to prove it. We know that there is one result, I forgot by whom, that even shows that Luby-Rakoff with the same number of rounds is insecure in the quantum setting. And I think no one has given any positive results on Luby-Rakoff.
Okay, let's thank Dominique again.